Welcome to the Databricks Lakeflow Jobs Playbook, the definitive guide to orchestrating production-grade data pipeline on the Lakehouse. So this session is going to cover everything from basic job anatomy to enterprise-grade CI/CD pattern. Whether you are migrating from Airflow, scaling an existing Databricks environment, or designing new data mesh architecture, these patterns come directly from production implementation. So key theme throughout our Lakeflow Jobs is not just a scheduler, it is a full orchestration engine that native to Lakehouse, meaning no external dependencies, no data movement overhead, and a unified governance through Unity Catalog. This slide captures the fundamental shift that justifies native Lakehouse orchestration. On the left, the fragmented world most teams live in, Airflow managing scheduling, ADF handling some ingestion, cron jobs for others, and all pointing us at S3 buckets and blob storage that feeds into a separate compute clusters. The result is fragmented governance, security complexity, and massive data movement overhead. Now, on the right, the unified Lakehouse model, one platform for storage, compute, and analytics. Unity Catalog provides a single governance layer across all workloads. The headline number matters here. 100 million plus job processed weekly, 14,600 plus active customers. This isn't a new product. This is battle tested at enterprise scale. This is the mental model to anchor everything else in the playbook. A Lakeflow job is a container. It holds multiple tasks that execute in a defined order. Now, inside a single job, you can mix task types, a DLT pipeline for streaming, ingestion, a SQL query for transformation, an AI/BI dashboard refresh at the end. Yeah. So the pro tip on nested orchestration is genuinely powerful. Jobs can trigger other jobs, which allows you to build modular team-owned pipeline units that compose into larger workflows. Think of it as microservices for data engineering. Each team owns their job, and cross-team dependency are managed through jobs, through job triggers rather than shared monoliths. Yeah, so that is an important distinction. Compute selection is one of the highest impact decisions you will make when designing Lakeflow jobs. The table tells the story clearly. Serverless is the recommended default for notebooks, Python, and Delta Live tables. It eliminates cluster startup latency, scale automatically, and removes infrastructure management overhead. Now, classic job clusters are still required for Java, for example, Spark, Subic workloads, legacy Spark jobs that need custom runtime configurations. The important limitation to flag here is serverless does not currently support continuous scheduling or default interval triggers with structured streaming. If you are running near real-time streaming jobs with those patterns, classic compute is still your path. Now, the shared compute strategy diagram below is critical for cost optimization. When tasks share a cluster, the cluster stays warm between tasks, eliminating the cold start penalty on every sequential step. For a 10-task pipeline, this can represent a 30 to 50% reduction in total compute time. The 3-trigger pattern, one sequential model. Know this code before you design any production pipeline. It's very important, this one. Time-based cron. The default choice for batch workloads with predictable cadences like standard cron syntax. Nothing surprising here. The data-centric, this is where it gets interesting. File arrival triggers fire when new files land in a path. Now, table updates triggers fire when a delta table receives new insert or merge. This eliminates polling logic entirely. So the trigger is the data connection. The continuous is the ensure exactly one active run at all times with exponential backoff on failure. Use this for near real-time pipeline where you need guaranteed execution without gaps. The concurrency queuing logic is essential operational knowledge. Triggers never get drops. If the concurrency limit is reached, then run queue for up to 48 hours. This is your protection against cascading failures from upstream delays. Control flow transforms job from a simple scheduler into a full orchestration engine. The left panel is conditional task execution based on upstream outcomes. So run task B if all predecessors succeeded, run task C if all failed. This is your failure recovery path. Route failed runs to an alerting task or a compensating action without building that logic into the notebook itself. So the right panel, if else branching based on dynamic expression. The example shows checking if the job start time is a Sunday. Let a single job handle both weekday and weekend processing logic. No separate jobs, no external orchestration layer needed. The expression language evaluates against job run context variables, giving you access to runtime, parameters, task output values, and more. This is where you replace what would previously have been Airflow branch Python operator patterns. The dynamic task values solve the problem of passing runtime state between tasks without external state stores. The pattern is two-step. Task 1 sets a value using dbt-utils.job.taskValue.set, typically a record count, a file path, or a processing status. Task 2 retrieves it using dbt-utils.jobs.taskValue.get with the upstream task key. On the right side, the user interface parameters panel shows the double curly bracket, double curly brace syntax for injecting task value directly into SQL files or notebook parameters. This is template substitution at runtime. Two patterns worth calling out explicitly. Dynamic JSON reference. Use the task.task_x.value.key.name to inject any task value into any downstream parameters. SQL output. Use tasks.sql.query.output.rows to pass SQL query result as an array of dictionaries to downstream tasks. This eliminates hard-coded parameters and makes pipeline data-driven by design. For each loop or how you scale a single job to process n entities in parallel without writing n jobs. Now the pattern here is like provide an input mapping table, typically a delta table or SQL query result that returns an array of dictionaries. Now for each container, iterates over that array, spawning a sequence execution of the contained notebook for each row. Then inside each iteration, reference the current row value using input.column_name syntax. Now, the critical operational guidance is the concurrency limit recommendation. Keep it between 10 and 20. Running 100 parallel iterations sounds appealing, but it will exhaust your cluster thread pool, and actually slow overall throughput. So 10 to 20 concurrent iteration typically gives you optimal throughput without resource contention. This pattern eliminates the anti-pattern of generating n separate job runs from an external orchestrator. Everything stays within a single monitored governed job execution. This slide shows how all the individual capabilities compose into a production end-to-end pipeline. The medallion architecture maps directly to Lakeflow job task types. Ingest is the Lakeflow Connect task pulling, for example, Salesforce CDC data into a bronze volume, and the refine is the DLT pipeline task handling deduplication, and the schema enforcement and incremental processing into silver. And the aggregate is the SQL or notebook task applying business logic and customer aggregation into gold. And then you have the serve, which is dashboard task triggering an automated AI BI dashboard refresh for downstream consumers. The key architectural insight here is this is entire pipeline from source system to business dashboard is a single Lakeflow job, one place to monitor, one place to configure alerts, and one audit trail in Unity catalog. No external orchestration layer, no cross-system debugging as well. The modern Databricks user interface has two features that fundamentally change the development and debugging experience. Now, the partial runs. You can select any subset of tasks, for example, in a DAG, and run only those tasks. If you are debugging task number 7, for example, of a 12-task pipeline, you don't rerun the whole pipeline. You run just task 7 or tasks 5 to 8. This is a significant developer productivity multiplier and dramatically reduces compute waste during development. And then you have the partial repair. When a production run fails at 6 of 10, you fix the issue and repair from task 6 forward. Tasks 1 to 5 that succeeds are not re-executed. The repair pick up exactly where execution stopped. The streamlined task palette on the right, a single searchable interface to add any task type, Lakeflow pipeline, notebook, AI/BI dashboard without navigating away from the DAG canvas. These three features together mean faster iteration, lower debugging costs, and more confident production deployment. The Databricks asset bundles are the answer to how do we apply software engineering practices to Databricks job management. Now, the three command workflow shown is the entire deployment lifecycle. Databricks bundle init scaffolds the project structure like notebooks, resources, configuration files, and then you have Databricks bundle validate, runs local syntax and dependency checking before anything touches your workspace. And then third is Databricks bundle deploy dev, which deploys all code and configuration to the target workspace. Now, the Databricks.yaml on the right is the infrastructure definition. It is a YAML. It is YAML, and it lives in Git. It gets code reviewed. It has full version history, job cluster, task dependency, compute configuration permission, all declarative, all source controlled. This is the migration path away from manually configured jobs that only exist in the user interface and cannot be reproduced reliably across environments. Now, this slide shows a complete CI/CD implementation using Azure DevOps, the full automation chain from code chain to workspace deployment. Now, the 5-stage pipeline, developer pushes to main branch in Git. Then Azure DevOps pipeline triggers via YAML configuration. Number 3 is the self-host Linux agent receives the pipeline trigger, and number 4 is Databricks CLI, runs bundle, validate and bundle deploy, and number 5 is like a target workspace synchronized with the new configuration. So the authentication setup code block is the practical detail that makes this work, writing the Databricks configuration file dynamically within the pipeline task using Azure Service Principal credentials stored as pipeline secrets. This means no long live tokens, no credentials in the code, and full auditability of the whole deployed what and when. And this pattern scales multiple environments by parameterizing the target flag, like tdev, tstaging, and tprod. Production observability requires two things: knowing when jobs fail and knowing before they fail. So alert destination, native integration to Slack, Microsoft Teams, PagerDuty, and email. Configure these at the job level. No separate alerting infrastructure needed. Yeah. So trigger events. So job start, job success, job failure, and task level failure. Task level failure alerts are particularly valuable. They tell you exactly which step in a 15-task pipeline failed without requiring manual inspection. And the duration threshold diagram is the proactive pattern most teams miss. So set an expected completion threshold at 50% of your SLA window. If exceeded, fire a warning webhook. Set a maximum completion threshold at 90%. If exceeded, the job is automatically killed and marked as failed. This prevents runaway jobs from consuming compute indefinitely and gives your on-call team time to investigate before an SLA breach. Now, streaming metrics. For streaming tasks, set a backlog threshold at task level. This is critical for detecting when a stream pipeline is falling behind its source. The single Databricks user interface is not sufficient for governing dozens of teams running hundreds of jobs across multiple workspaces. You need a custom observability layer. Now, 3 data sources enable this. REST API provides granular near-time data, current runtime status, task level details, job configuration snapshots. So use this for operational dashboards that need live data. And you have the system tables. The system.lakeflow schema contains historical jobs run data with versioning. So use this for trend analysis, SLA tracking, and identifying jobs with execution time degradation over time. And then you have number 30, Databricks AI BI dashboard. Unify the REST API and the system tables data into a single governance dashboard that workspace admin can monitor across all teams. So these 3 dashboard panels shown represent the 3 failure modes worth tracking proactively: daily success, failure rates, and execution time degradation trends, and compliance gap, which is job missing schedules or running on outdated Spark version. So this is the final slide, and it is actionable summary. So 5 practices that separate production-grade Lakeflow implementation from ad hoc job configuration. So optimize compute, always evaluate serverless first for sequential task pipeline. Use shared compute to eliminate cold start latency between tasks. Now, debug smartly. Partial repair are your most powerful debugging tool in production. Partial runs are your most powerful tool during development. So never rerun a full pipeline when only a subset of tasks needs attention. Now, pass context. Use dbt util.jobs.task value for inter-task state and JSON reference for dynamic parameters. Hard-coded parameters are a technical death trap. So automate a deployment. If a job for configuration exists only in the user interface, it is not production ready. Every job should be defined in a DAB YAML file, committed to Git, and deployed through a CI/CD pipeline. Now, govern centrally, build a custom observability layer using the REST API and system tables. The Databricks user interface is a starting point. Enterprise governance requires a purpose-built dashboard. These 5 practices are the foundation. Built on them, and your Lakeflow implementation will scale with your organization. Thank you for listening. This is the end of this Lakeflow job series, and see you next.